Welcome students. In this session, I will be talking on molecular velocities of gas. In the last sessions, we have seen Maxwell's distributions of velocities and energies, its graphical representations and various derivations. Okay. So, in this sessions, as I already told in the last session that this graphical representation means a lot to different velocities of the gas molecules. Okay. So, from the graph we can evaluate most probable velocity, average velocity and root mean square velocity. Most probable velocity is actually the velocity possessed by maximum fraction of gas molecules in a gaseous system. That means it represents the peak of this Maxwell distribution curve, and the average velocity is actually the arithmetic mean of different velocities of all molecules that forms the average velocities. It have a mathematical representation that I am taking N1, N1 means particular fraction of gas molecules with C1 velocity, N2 is particular fraction of gas molecules with C2 velocity and etc. That values we are adding and finally finding its average so as to get the average velocity. Okay. And the other velocity that we get from this Maxwell's distribution curve is that it is root mean square velocity, and that is the square root of means of squares of different velocities. That is, this average velocity we can square, and that square we are taking this square root so as to get the RMS velocity, and it is represented in such a way that N1 C1 square, that is the N1 fraction of molecules with the C1 velocity, and the C1 velocity is squared, and for each case this is repeated and the whole thing's average, its square root is taken so as to get the mu RMS. Okay. But actually this is not possible to each time calculate every fraction. We cannot find correctly what is the exact fraction of a gas molecules having a particular velocity. So, we need to find some other mathematical expression in order to calculate such velocities for a particular gaseous system under study. Okay. So, that for that first we will go with the most probable velocity. Okay. So, now we are going to derive what is the mathematical representation for most probable velocity. Okay. We have the Maxwell expression, that is Maxwell distribution of velocities, that is 1 by n dn c by dc, which is equal to 4 pi m divided by 2 pi RT raised to 3 by 2 e raised to minus mc square by 2 RT into c square dc. We have seen its derivation in the last section, isn't it? Okay. So, from this relation we are now going to find out what is the most probable velocity. Okay. And I am just modifying this relation in so that I am introducing two terms A and B. Okay. Here A means m by 2 pi RT raised to the power 1 by 2 and B is equal to m divided by 2 RT. Okay. I am substituting these A and B to my Maxwell's distribution relation so as to get the modified equation as 1 by n dn c by dc, which is equal to 4 pi a cube e raised to minus b square c square dc, okay, which can be written as P of c. P of c means the probability of the gas molecule to have that particular velocity. Okay. So, in order to find the RMS velocity, I need to give a condition, that is P of c equal to 0. P of c equal to 0 by max, in lower classes we have studied that first derivative of a particular function, if it is equated to 0, we get the most probable value of that particular function. Okay, the same condition we are applying here, because we know this Maxwell distribution curve, the function with the highest value is the most probable velocity. So, if we find the first derivative of this point, if this function, and if we equate it to 0, we get the peak value. Okay. So, that we apply the condition P dash c is equal to 0. So, here we have the Maxwell expression, that is 4 pi a cube is a constant, and that into a, I am taking a into b, that is we know that the derivative of a product is first into derivative of second, second into derivative of first. So, that we are applying the same thing over here, 4 pi a cube first into derivative of second, that is e raised to minus b square into derivative of second means derivative of c square, which is 2c, plus second is c square into derivative of first, that is derivative of e raised to minus b square, which is e raised to minus b square into the derivative of this exponential term, okay, that is minus b into 2c, and this is equated to 0. Okay. And in order to fulfill this condition, we cannot equate this constant equal to 0. Instead, we equate this part of the equation equal to 0, that is 2c e raised to minus b square minus 2c cube e raised to minus b square into b is equal to 0. Okay. Now, I am taking the common terms outside, that is 2c e raised to minus b square into 1 minus b square is equal to 0. Now, this also form a constant, so that I can take this part equal to 0, that is 1 minus b square is equal to 0. Okay. That is 1 is equal to bc square and c is equal to 1 by b. Before that, we have, at the beginning we have substituted b is equal to m by 2 RT. So, we are introducing that term here, that is we get c is equal to root of 1 by m divided by 2 RT, and if we take this denominator part of the denominator to the numerator side, we get the final, which is RMS velocity is equal to root of 2 RT by m. So, this is the expression for the RMS velocity. So, here we need to understand only the molar mass of the gas, and R is the real gas constant, T is temperature. From this we can easily estimate what is the most probable velocity of the gas molecule. Now, we shall look what is average velocity mu bar. Okay, from the graph we could find that the average velocity is actually we need to find, that is taking a particular velocity, extrapolating and finding the fraction, again doing this repeating for every values of velocity, and then we need to find the average of the particular gas, what is the average velocity of that particular gaseous system. Okay. So, avoiding that, by Maxwell's relation we are now going to find the mathematical expression for this average velocity. Okay. We have the Maxwell relation 1 by n dnc by dc is equal to 4 pi a cube e raised to minus b square into c square dc, where a is substituted for m divided by 2 pi RT raised to the power 3 by 2 and b equal to m divided by 2 RT. Okay. And now, we know that to find the average velocity, we need to integrate the whole area which is under the graph, right. So, we are applying that condition to our Maxwell's distribution relation. Okay. That is average velocity is equal to integral 0 to infinity, that is from origin, that is 0 velocity to what that last velocity is that. So, we integrate 0 to over the rate 0 to infinity into c into dnc by n will give the average velocity. Now, we are multiplying and dividing with dc. Okay. So, that we get it as 0 to infinity, integral 0 to infinity c into dnc by dc into dc by n. Okay. Now, we are substituting our Maxwell relation to this, and mu average will be written as integral 0 to infinity c into 4 pi a cube e raised to minus b c square into c square dc. Now, we are going to solve in order to understand what is mu bar. Okay. Mu bar is equal to, rearranging the equation, that is c into c square can be written as c cube, and in the next step we are assuming z is equal to c square, then we can write dz is equal to, that is dz means differentiating z, that is dz is equal to differential of c square, that is 2c into dc, that is written over here, and then we are substituting this assumption into our relation. Okay. So, here 4 pi a cube is at 3 by 2 because we have c cube. So, we have taken z equal to c square, then in order to substitute for c cube we need to substitute as z raised to 3 by 2 into e raised to minus bz, and here it is dc. So, we need to substitute for dc, and here we can substitute as, because by here it is dc equal to 2c into dc, that is dc is equal to dz by 2c. Okay. Now, again substituting for this, we can write it as dc is equal to dz divided by 2 into, for c it is will be root z. So, that is substituted over this part. Okay. And in the next step, we are resolving, and we can write the equation as 0 to infinity 2 pi a cube z e raised to minus z dz. That means we are cancelling off here terms like 4 by 2 and all, we are getting 2 over here. Okay. And taking the constant outside of the integration part, we can write it as 2 pi a cube integral 0 to infinity z e raised to minus bz dz. Okay. And now again I am assuming that bz is equal to k. This is done in order to find out the value of that exponential term. Okay. And here, as I am assuming k is equal to bz, then dk can be written as dk is equal to b into dz, that is written over here, and then substituting these assumptions to this equation, we can write it as mu bar is equal to 2 pi a cube integral 0 to infinity z can be replaced by k by b e raised to minus k into dk by b, because we need to substitute for dz. So, dz will be dk divided by b. Okay. And now again taking b terms outside, we can write it as 2 pi a cube divided by b square 0 to infinity k e raised to minus k dk. Okay. You might have studied in your lower classes that it is exponential x e raised to minus into dx is actually gamma 2. Okay. So, we can substitute that part with gamma 2, and the value of gamma n is actually n minus 1 factorial. So, it is gamma 2, that means 2 minus 1 factorial, that is 1 factorial which is equal to 1. So, this whole thing reduces to mu bar equal to 2 pi a cube divided by b square. Okay. And now, we know that we have substituted at the first a equal to m divided by 2 pi r t raised to 1 by 2 and b as m divided by 2 r t. So, we are taking this thing into our equation so as to get the final form. So, also a can be written in terms of root of b by pi, because when we relate these two equations, the difference is that a is equal to root of b by pi. So, substituting this value over here for a, we can get mu is equal to 2 pi b square into b raised to 3 by 2 divided by pi 3 by 2, because we are substituting for a cube over here, which is can be related to common terms are cut off, and we can get 2 divided by b raised to 1 by 2 and pi raised to 1 by 2. That means 2 divided by root of b pi. Okay. Again we are now going to substitute for this b, and it is 2 divided by root of m divided by 2 r t into pi. Okay. So, taking the denominator of the denominator to the numerator side, we can write it as 2 root 2 r t by root of m pi. So, taking 2 this into this square root, okay, it will be 2 into 4, square root of 2 into 4, which is square root of 8. So, we get the final expression for the average velocity as mu bar is equal to root of 8 r t by pi m. Okay. Now, next we will move to the root mean square velocity, that is mu RMS. Okay. As I said earlier, mu RMS is actually the square root of average velocity, and that is expressed over here, that is mu RMS is mu square the whole raised to 1 by 2. Okay. So, starting with mu square, I am starting with mu square, that is we are integrating 0 to infinity c square dnc by n, which is equal to integral 0 to infinity c square dnc by dc into dc by n. Okay. Again applying Maxwell relation to here, we can rewrite it as 1 by n dnc by dc, which is equal to 4 pi a cube e raised to minus b square into c square dc, and then writing the common terms together. Okay. Mu or applying this equation to over here, we can write it as mu bar square is equal to 0 to infinity c square 4 pi a cube e raised to minus b c square into c square dc. Okay, I am resolving in steps, that is c square and c square can be written as c4, that is written in the next step. Now assuming c square, here I have c square into c square. So, c square is assumed as z, then dz, the derivative of z will be 2z dc. The same thing we have done previously. It is similar steps we are going over here also, that is mu square is equal to 0 to infinity 4 pi a cube z square e raised to minus bz dz by 2z. In the previous case also, we have done similar way, that is dc is equal to dz by 2c according to this assumption, and we are again substituting this c, so that we can write it as dc by 2 root z, dz by 2 root z, that is being given here. Okay. And again simplifying, we can write it as 2 pi, I am taking the constant term outside, so that 2 pi a cube root of integral 0 to infinity z raised to 3 by 2 into e raised to minus bz into dz. Okay. Again, in order to find the value of this exponential factor, I am considering this bz is equal to k. That means dk will be equal to constant b into dz. Okay. And again substituting these values to here, I can write it as mu bar square is equal to 2 pi a cube 0 to infinity z 3 by 2 can be substituted with k 3 by 2 divided by b 3 by 2 into e raised to minus k dk by b, because d is it, we have to substitute for dz, that can be written as dk by b. Okay. And I am taking this b 3 by 2 to outside, here also I have b. Okay. So, taking that we can write it as b raised to 5 by 2, and rest every part is written as such. And now this k raised to 3 by 2 e raised to, or by max we have studied x raised to 3 by 2 into e raised to minus x dx is actually gamma 5 by 2. Okay. So, gamma 5 by 2 is actually 3 by 2 into 1 by 2 into gamma 1 by 2, and gamma 1 by 2, now we need to substitute the value of gamma 1 by 2, which is actually pi. Okay. And we are taking this reducing the common terms, and we are getting finally 3 by 2 pi a cube b raised to 5 by 2 into root pi. Okay. And we are now coming to the final session, that is a equal to, so that we got a, we are now substituting a equal to b root of b by pi to this previous equation, so that we got average velocity, the square of average velocity mu bar square is equal to 3 pi divided by 2 b 5 by 2 into b 3 by 2 divided by pi 3 by 2 into pi. Okay. Cancelling off the common terms, we get mu bar square is equal to 3 by 2 b. Now, the rest part is that we need to only substitute what is b. Okay. So, that we get the final equation as pi square is equal to 3 by 2 into 2 RT by m. Okay. And that is 3 RT by m, and as I said, root mean square velocity is the root of square of this average velocity. So, we need to apply square root to both sides in order to get the mu RMS. So, mu RMS is finally root of 3 RT by m. So, finally, we got the expression for mu RMS also. Now, we are going to compare the values of different velocities. Okay. That is, we have average velocity, mu RMS velocity, and most probable velocity. So, most probable velocity is to mu RMS, average velocity is to RMS velocity can be written, that is, we are taking just and relating their mathematical expression. So, that it is 2 RT by m is to root of 8 RT by m is to root of 3 RT by m. Actually, this RT by m can be written in terms of k, k is Boltzmann constant and m is mass of one molecule. Okay. And the relation, that is, this relation can be reduced to, because we have common terms kT by m, or here also RT by m. So, we get it, which is equal to root 2 is to root of 8 by pi is to root 3, and that is 1.414 is to 1.595 is to 1.732. From the values itself, we can see that most probable velocity is the least value and mu RMS is having the highest value, and the same thing can be correlated to our graph, isn't it? That is, most probable velocity is having the lowest velocity value and our RMS value is having the highest velocity value. Okay. Now, we shall go through some problems. Usually these problems are very important in terms of certain competitive examples, including CSIR, NET or GATE or something, department aptitude text, etc. So, I am going to important two problems. Okay. The first one is that for a hydrogen gas, calculate the root mean square velocity mu RMS, the average velocity mu bar and the most probable velocity mu alpha at 0 degree Celsius. Okay. Here it is given, the case of hydrogen gas, isn't it? So, the mass of hydrogen gas is actually 2 gram, isn't it? Okay. So, we can write in terms of SI unit, it is 2 into 10 raised to minus 3 kilogram per mole. Okay. And first we are going to start with RMS velocity. RMS velocity, we know it is equal to 3 RT by m. Okay. And here we know that R is equal to 8.314 joule per Kelvin per mole, isn't it? So, now we need just to, and also one more thing I forgot, T is given as 0 degree Celsius, which is equal to 273 Kelvin. Okay. Now, just substituting these values, we can get the RMS velocity, which is 3 into R is 8.314 into T is 273, the whole divided by mass is 2 into 10 raised to minus 3. Okay. That means we get the value as 1.8 into 10 raised to 3 meter per second, and this is the mu RMS velocity. Okay. Now, we will go to the second part of our problem, that is to find the average velocity. We know that average velocity is mu bar is equal to 8 RT by pi m. Okay. Substituting the values, we already know that 8 into R is 8.314 into 273, the whole divided by pi is 3.14 into m is 2 into 10 raised to minus 3. Substituting this, we get the value as 1700.6 meter per second. Okay. Now, the third part is to find the most probable velocity, that is mu alpha, which is equal to root of 2 RT by m. Okay. Here directly substituting all the values we have, that is 2 into 8.314 into 273 divided by 2 into 10 raised to minus 3, which is equal to 1506.56 meter per second. Okay. And first we have already derived that mu RMS is equal to 1.8 into 10 raised to 3 meter per second also. So, now comparing these values, we can see that the mu RMS value is highest, that is 1.8 into 10 raised to 3 meter per second, and the next highest is mu average, and the least value is for mu alpha, that is for most probable velocity. Okay. So, from this equation or this problem, the values can be correlated to our Maxwell relation, Maxwell distribution of, that is graphical representation. Okay. So, these values are consistent with that what we have seen so far. Okay. So, now I will move to the last one more problem. The problem is to calculate the temperature at which the average velocity of oxygen equals to that of hydrogen at 20 Kelvin. That means the average velocity at 20 Kelvin is same for average velocity is same for oxygen and hydrogen's temperature is given as 20, and we need to find the temperature of oxygen what is that temperature in order to meet that average velocity, same for hydrogen and oxygen. Okay, we know that the average velocity is mu bar is equal to root of 8 RT by pi m. Okay, since 8 R and pi m are constants, I can write it as mu bar is directly proportional to root of T by m, or simply it is proportional to T by m. So, now I am relating the temperature and masses of oxygen and hydrogen in order to understand what is that temperature where the oxygen average velocity equals to that of hydrogen. That is T1 of mass of oxygen is equal to T2 of mass of hydrogen. Okay. And this can be written as T1 mass of oxygen, a particular oxygen molecule we know it is 32 gram per mole, and that of hydrogen it is 2 gram per mole. So, equating this we can write it as T1 equal to 32 divided by 2 into T2. Okay, T2 we know the temperature as 20 Kelvin, and 32 by 2 is 16, and that is 16 into 20 Kelvin, which is equal to 320 Kelvin. Okay, so this is the answer. So, we got the final answer as 320 Kelvin. That means the oxygen at 320 Kelvin, it will be having an average velocity which is equal to that of hydrogen, which is at a temperature of 20 Kelvin. So, with this problem I have come to the end of this session. So far we have discussed different molecular velocities of gases like most probable velocity, average velocity and root mean square velocity. We have seen how the mathematical derivation is done, and also we have done some problems. Okay, so hope this part is clear to you. So, thank you.